All right, Siri, I think we should go over the two types of problems that you're going to encounter with KSP. In this first set, you're going to be given the solubility of the ionic compound. Typically, this is going to be in moles per liter or molarity, and you're going to be asked to calculate KSP. So if we take a look at this answer key, let's just take a look at some of the key steps to solving one of these problems. The first step must be to write the dissociation equation for the ionic compound as it dissolves. Remembering, we start as the solid dissociates into the ions, which are now charged. Now, the key thing to remember about KSP is that we're making a saturated solution. And when we make a saturated solution, the rate of dissolving and the rate of crystallizing becomes the same. So remember, when we're talking about equilibrium, we talked about in previous examples the rate of the forward reaction being equal to the rate of the reverse reaction. So we still have to have these opposite processes reaching a point where they're equal. And since this is a physical change of dissolving, we're comparing like dissolving versus coming out of the solution and going back to being a solid. So when we have this equilibrium and we make this saturated solution, there's some implications for us mathematically. Now, setting up a problem like this using an ice diagram is a good way for you to visualize what's happening. So first, this number, this 1.09 times 10 to the negative third moles per liter, is the amount of the copper chloride that would be put into the solution. Remember, by definition, solubility is the maximum amount of solute that will dissolve in a given amount of solution to make a saturated solution. And we learned this way back in the solutions unit. So according to what we know, this number here is the maximum amount that we need to make a saturated solution. So we add this amount of solid, which is 1.09 times 10 to the negative third moles in 1 liter. Now, we have to understand that all of the solid has to dissolve. So all of it gets used up and we go to 0, which I know is a little bit strange because previously when we've talked about equilibrium, we said you had to have something of everything at equilibrium. This is a little bit different. So in this situation, we go to 0, but the important thing is the coefficients now in our balanced equation will always follow the change line and will then tell us, oh wait, now I know how many moles of copper ions were in the solution per liter and how many moles of chloride ions were in solution per liter. So I'm going to follow the stoichiometry. Now, some students might say like, oh, no, why Miss Smith is going through all this work. I know it's in a 1-to-1-to-1. I'm just going to use the same number twice. Well, some of these get a little bit trickier and you want to make sure you're not forgetting something. So using the ice diagram is like one way to really remember what's happening. All of the solid dissolves. The amount of each ion is predicted now just using our regular old stoichiometry. So once we have that amount of each ion, we're going to plug that into our equilibrium expression, which is down here, and then we're going to solve for KSP. So in all of these problems on the first page, we're just solving for KSP. Now the question that you were asking me about is a little bit different, and that's because in the balanced equation, we do not have a 1-to-1 ratio. We have a 1-to-2 ratio. So this means even though the solubility of the solid was given to us, that translates into different amounts of each of the ions. So if you remember way back in solutions, we did some work like this. The question would be like, given the concentration of calcium chloride, what's the concentration of chloride ions in the solution? And we had to take into consideration that mole ratio. Same thing. So here the ice diagram is really helpful for you to recognize that, yes, it's a 1-to-2 ratio. Now I have these two concentrations, which are my products. I'm going to put them into my equilibrium expression here and then solve for KSP. So in this first scenario, it's important that you know the concentrations of each ion in the solution so that you can plug them into the KSP expression. Now, if we move ahead to the second set of problems, in these second types of problems, you'll have the KSP, and now you need to work backwards to solve for those unknown concentrations. And there's a couple scenarios that will occur. In one scenario, which we can see in number 1, the ions are in a 1-to-1 ratio on the product side, which means if one of them is X, the other one has to be X, because we're not starting with any amount of this. So when we produce those ions, they're in a 1-to-1. So in this problem, since both the ions are X, we write them as X and kind of combine everything together. This is an X squared idea here. And then we have to solve for X by taking the square root. I didn't show that intermediate step in there, but mathematically, you have to realize that this is equal to X squared. Now, once we solve for X, which is going to be both of these numbers down here, statistically using stoichiometry, we have to realize that that was also the original concentration of my solid, or the original amount of solid that I would need per liter to make it saturated. Now, the number 2 that you were mentioning is a little bit different, and we have to consider, since the ratio is not 1-to-1, it's 1-to-2, we have to play around with our values for X. They're no longer X and X. And now one of the things that I saw on your worksheet was you had it as X and X squared. You had forgotten that the 2 was also the coefficient, which meant that not only would you have to square it in your expression, but the concentration would be double the concentration of the magnesium. So that was kind of the missing thing that you forgot in your number 2. And these are really the two scenarios. In one scenario, you'll have 2 X's, and then you'll be kind of using the square root to solve for X. And then in this second scenario, you have an X and a 2X, which results in having, when we combine all those terms together, 4X cubed. So this means you're going to have to divide both sides by 4 and then take the cubed root to solve for X. So, I'm not sure if you know how to take the cubed root on your calculator, but it's under the math button under your calculator. If you go to the math button and you scroll down, I think it's like the 4th option, that's how you do cubed root. And as you can see, I have this note here that sometimes I have to remind students how to do it because it's something that you haven't done in a while, okay? So hopefully this will help. This answer key is opened, so take a look at it and go through it and keep asking me those questions. I'll see you tomorrow, hopefully. Cross your fingers.